Okay. Okay, so welcome to the third lecture in neural networks and deep learning. After, we did more the introduction the first week. You had hopefully some practical experience last week. Today, now we want to go into the next step. And as I said, we want to now look at different architectures. Before we will very concretely look into the different types of architecture, today we wanted to address why we need these different architectures. So why can't we solve everything just with normal feed-forward networks? And therefore, we will look into how you want to apply neural networks, what types of data you want to apply that on, which will then motivate us on what is needed for different types of architectures in order to handle this type of data. And that's why this is a bit titled different types of model types and models where you're using deep learning models. In order to do that, what we will today do is we start with the standard classifier and feed-forward network that is trained in a supervised way to classify some things. There we will look a bit how we'll handle data, because that is, of course, essential in all the cases. How can you represent different types of data? And that will be a bit the first part. We'll do that at some examples, and it nicely shows that as the big advantage of neural networks, because you have to do this mapping of the data into some numerical values, but then you can do just the standard feed-forward network and always apply them to very, very different types of tasks. Once we have that, we'll look to open challenges and why maybe not everything can be solved with a normal feed-forward network, and what are other things which are difficult to handle with them. Based on that, we will look then into three main parts of what needs to be extended or what needs to be handled. The first is that you might have data which has some structure, and you need to somehow represent this. We'll start with, or a common thing is sequences. So there's a lot of applications where you have sequential data. So how can you handle sequential data? And then we'll also do more complex structures, 2D like images, or then graph structures and things like that. Then the second question, if you now need networks to handle this type of input structure, the other question is what type of mapping do you need to do? Like the standard is like a one-to-one mapping that your input and output has the same type of structure. In a classifier, you have a fixed size representation as input and as output. However, for a lot of applications, you might need something different. We'll look there at three things. One is it might be like you need some type of pooling to reduce the structure to have a more simple structure. But then you also might want to do the opposite. You want to generate some type of structure which will add you some more difficulties. And we'll look how that can be implemented. And then there's another thing called Siamese networks, where you want to have an ability to not only have a predefined set of things that you can predict, but be more variable in there. And finally, we'll look at a bit how you train your system. The default is you have some supervised data, but it might not be always there. So other applications or ways to train it is more in an autoencoding or in a GAN style of network. So that should give you a bit an overview of where you apply neural networks. And then, in the next weeks, we will look how you can now think of other architectures which can address a bit these types of challenges. So with that, let's start with the first thing, which is the classifier, and let's have a look how a standard classifier works. So if we're having a typical classifier with a neural network, what we have is we need an input to our network. This should be first a fixed size representation, and typically it's then an n-dimensional vector. Can be real values, it can be integer values, but in generally that is what you put in here. So if you want to use a neural network, we have seen that in the introduction, what you need is some type of vector input here, which represents your input. Then you have your neural network, which is like the learning and learns the mapping to some other type of fixed size vector. So again, our output is like an n-dimensional vector, which represents somehow the output. And again, we need to have then, of course, a mapping. We maybe want to address tasks where there's not a vector input, but some other semantic meaning to it. So you need to have some of this mapping from the vector to the semantic meaning. And when you think about training these models, what you need is you need pairs of input and output pairs. You put the input in, you generate the output, and then you check how good your error is or your result is, measure the error and train it. So in order to train it, you need labeled data and input output. And although this is like first might be quite restricted, you're saying you can only like somehow map some vector to another vector. The nice thing is with this, and with some idea of how to do the representation, you have already a quite powerful tool, and then we want to look into it now. So the main question is, of course, the data representation. So if you have some type of data, it's not always vector data. So the question is, how can you do this mapping from your data into some vector, and then again from this vector to your result? And we'll have like 4 examples or so to see how these things work. Let's start with a typical machine learning examples, and that imagine you want to train a weather forecast. Now this is not a complex model, but a very, very simple model. You have today's temperature, you have yesterday's temperature, today's wind, today's cloud cover, and today's rain, and you want to somehow predict tomorrow, is it rainy, sunny, or cloudy? And I guess all of you can easily imagine, it shouldn't be too difficult to collect this type of data. It will not be a very good type of weather forecast model, but it will do some type of weather forecasting. We're knowing, like if you know today's weather, you have a quite good approximation of things, how things are tomorrow. So here we see already, we're putting in this type of data, we're putting in some type of output data, but how can we now use a neural network to do that? These are not just like numbers. I mean, your output is like 3 classes. You have temperature, which might be numbers, but how do you combine them into having one single? So you have very different types of inputs here, and you want to have, in the end, one n-dimensional vector, which does that. So how can we do that? So the easiest thing is, of course, if the data is represented as numerical values. Like, for example, here, today and yesterday's temperature, the wind, and rain, for example, which is all numbers. You could directly take the numbers. What is typically done, it's again like more from the learning perspective. If you remember your activations functions, they are somehow the best, like around, or the gradients are the biggest around 0, -1, and 1. So it somehow makes sense to normalize them. There's now different ways you can normalize between 0 and 1 or -1 and 1. That depends on your activation function. But generally, some type of normalization is helpful, because if you have 2 big values, you might not have like or a good learning in there. Which means, so you take some minimal value of your variable, some maximum value, and then you map it to the new value, which is its value minus the minimum divided by x max minus x min. So in the end, your results will all be between 0 and 1. And so you have hopefully a better type of input. So in this type, the temperature from yesterday will be 0.75. The temperature, from today, from yesterday will be 0.16, and the wind will be 0.06. So that is quite straightforward. Of course, the 0 and 1 is only for your training data. In your test data, you might get values which are a bit bigger and larger. Again, the hope is, of course, if you have enough training data, you should not have completely different values. Anyway, the model will not work if you are training on data where the temperature is always 0 to -5 degrees, but then you're testing it on 20 to 25 degrees. That will not work. So with this normalization, you're somehow still keeping it in the same area. Quite similar, or not quite different, but like also straightforward. It is possible to also encode categorical values. what you there typically do is like what is called the one-hot encoding. And there it is important that you have, of course, a fixed number of categories. So in all this, typically it doesn't work that you're now in the testing, you might have some other categories, then this doesn't work. On the other hand, if you're just adding a category, you have no idea what that means, then of course it's also not helpful. So in machine learning, it only works if you have seen something similar before, and therefore this type of representation makes it very straightforward. So if you have, like here, 5 values, you can represent them in 1, 2, 3, 4, 5, and you're doing this type of one-hot encoding, which is a 5-dimensional vector where there is like a 1 at one position and the 0 at all of the others. This looks first a lot less efficient than just taking an integer like 1, 2, 3, 4, 5 and using them, but it has somehow one advantage, depending, of course, on the use case. What is an important property of this one-hot encoding?
It could be better for training.
Why?
Because you have these different output values, and you could just take the subtraction value, and you know this output should be lower than the others.
Don't completely get now the. So you subtract 2 values, and then so 1 and 2, and then you get 1 minus 1 or something like that.
You know that this certain label, for example, 1.
Yeah.
You know that this output node for 1 should be rather high, and the others should be rather low. And just with this subtraction with this one-hot encoding, you could train this network to put exactly that output node to 1 and the others.
Yes, yes, that's I think in the right direction. So yeah, you're more focused on that. That's more on the output node where, I mean, you can use that both for input and output. And yeah, that is right for the output in some way. There was another.
I think it's easier to calculate the error, or because we have 5 inputs and instead of 1, so it's easier to differentiate for every input.
Yes, I think it's, I mean, yeah.
You can have like specific weights for each value. So it's better for training also. Like for the input, each of these values can be like one node. So each node has its own weights.
Yes, so when you're more independent, you can also say it in the way that, yeah, the distance is the same. So you're not putting any bias on it. Otherwise, if you want to put bias on it, it might be more important to do real values. But then you're saying that 1 and 2 is more similar than 2 and 3. And now that depends heavily on what categories you have. Some categories, if it's like sunny to cloudy, maybe it's related. But if there's rainy, cloudy, and some others, it's not really clear how they are related. So is really cloudy more similar to very cloudy, or is it that should be the same distance than to rainy? So if you don't really understand the distances, here you have individual distances between all of them, and you can really learn each of them how important. You can also, for the error, as you said, you can say maybe some errors should be worse and some should be not as worse. So you just have a lot more flexibility. Of course, at a cost, because your input is now, we have 5 inputs and not 1 input. And we know that like you need parameters for each of them. So normally the number of parameters you have depend on your input size. And therefore, if your input gets very large, you'll have a lot of parameters, and that might be then no longer efficient. But in generally, that is why categories, we are not putting any specific bias on how things are similar, how important some things and other important things. And we can just learn that by the model. And that's a big advantage of using some type like a one-hot encoding. Then the nice thing about now neural networks is, in order to like use all these information, that is super easy. What you can just do if you have more input, you're just concatenating them to them. Of course, it's fixed, we have defined, but you train now a new model which also has maybe the the wind from yesterday or the temperature from the average temperature in the last 3 days, you can just add it to that. You're not putting any bias on how these are related. If you think about a feed-forward network, they're just all connected to that. So you can just add any information that you think is important to your input, and the model will learn how to integrate that. What is the relation between the input? You're not like doing that by hand, but you're learning that automatically. And that, of course, makes it easy. So if you think of some traditional statistical model, you had to like make a story how their inputs are connected and how you can predict them. In this type of classifier-based approach, you can just stack all the information you have in there and let the model learn which one of them are important. And of course, not perfectly, but in generally, if you add things which are which don't have any correlation, which are not helpful, it shouldn't really matter that much. I mean, there are some side effects. The more inputs you have, as I said, the more parameters, you might have more overfitting. But in general, the model can also learn to just ignore information which are not there or not helpful. So the nice thing is you can just put in information you think could be helpful and then let the model learn how to integrate that. So that is now in the input. On the output, you can mainly do the same thing. That's again nice. So also for categorical values, you can do the one-hot encoding, saying which one is the right solution. And for numerical values, you can do a regression. So you're not doing if you're not doing now a weather forecast, but more a temperature. The only thing is you do at the top, you maybe do a regression model which predicts the temperature. You can also do it even jointly. That's again, like not only on the input, you can combine things, but you can also at the output combine things to jointly predict several things. Again, it might be better if a model jointly learns something to again model some dependencies and not like predict each one of them individually. So like fusing information on the input or in the output is very easy. You can just concatenate with vectors to each other and then get like some of these types of models. Good. Any questions to the first two examples? Yes?
How does this exactly work? Because now we are putting lists through the network instead of values. Like, how do we then calculate like the values for K1 and K2, for example?
For, I mean, we're not putting lists. So what we're that's a very good point. So we are assuming here, I mean, the image is like you have 3 inputs. So now here you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inputs. So your input would be 10 nodes in this type of picture. So you're always assuming an n-dimensional input. And then, I mean, you can view it as this matrix multiplication. So that defines the one size of your matrix. Is a feed forward is a matrix, and then you put it in there.
So you still need a fixed size input.
Yes, that's a very important point. So standard feed forward networks only work with fixed size inputs. So you once in the end, by defining your network, you're defining what input vectors you use, and then you cannot later add, oh, I think this is also add, so I add now something. Because the model does know there are no weights connected to it, so the model does know how to treat them. So that's a very important point, and we'll come to that today, how that is a challenge. You can do even more. For example, if you want to now have a different use case, let's assume you do object detection on an image. A very straightforward or very simple solution could be, again, just a feed-forward network. You would have to somehow rescale your image to n times m pixels. So again, that is the important. You have to have the same type of input always. Then each pixel has around like 3 values, like the red, blue, green, and blue part, so RGB. And then you could have a list of 3 times n times m values. You linearize them, maybe normalize them, and again, you have an input which you can put in to then train your object detection system. And for your object, you might have, again, object classes. So you have a class, a cat, dog, human, car, or something, fixed size, important, one-hot encoding, and you can do your type of object detection there. So it's again a normal classification. We see now we can already put with a very basic one very different things into our network. We can put images, temperatures, information. So a lot of things can be represented as numbers by just using that in numerical values or in categorical, and then you can put them in and let the model learn what that is. We'll come in a second, another say, like some slides why this might not always be the best approach to use a full flavor, but from an architectural point of view, it could work. Yes?
So with every discrete object be represented as a one-hot encode.
Yes, yes. So if you have this type of discrete objects you want, that's why I said you need to have a fixed size. So you cannot say, oh, detect anything or like, we'll have a bit of architecture which can do that later. But if you have this type of architecture, you have to predefine, oh, I can do 100, 1000, 10, any number of objects, and then in training, you only train these types of objects, and you can only recognize that. And I mean, that is done in a lot of the image networks, even for a long time. There's no open class recognition where you can also do other things, but there's a lot of work on doing a predefined set of classes which you want to classify. And even other things can be very, very similar. Just think about speaker identification. So you want to know, have a 10-second audio snippet, and you want to know who's speaking. So again, if you have 10-second audio snippet, it's like a fixed size. So you can again put that into some type of fixed size representation there, put it through the network, do your speaker ID. Again, this of course only works if you have a predefined number of speakers. So it doesn't know that you compare it to some samples and find the most similar one, but you have like, oh, I trained it on my company, which has 20 people, and I want to know which of the 20 person is speaking, maybe 21st to say like, oh, none of all of them. I mean, that's now your definition of the labels, and then you can train the model to exactly do this type of task. Good. So this is how you can use data representations to really apply in your networks to quite a big variety of different types of tasks. Before we are going now to the open challenges and what are advantages or disadvantages, do you have any questions? Yes?
How do we choose number of hidden layers or hidden nodes?
Yeah, that is now a bit the black magic behind that. I mean, a good starting point is typically what other people have tried, and then starting from that to change. There is work on like AutoML or so, which tries to do a large search on possible hyperparameters and optimize them, which of course comes now at the question, how expensive is it to train one classifier? If you can train one classifier fast, you can do tests and search and do like different algorithms to search what is a good thing. If you train a really big model, which takes you 3 weeks to train just the one model, because you cannot do the search, and then it somehow makes sense to start with something where you have reasonable good assumption that. Again, the hope is, in most cases, it's not like that. It really depends whether you have one node more or less or one layer less. Typically, the bigger they're getting better. At some point, you have overfitting, so there it doesn't work anymore. But yeah, it depends on your data size and on your feature space size that you should have a good rule for how many you use it at the time. So what are big advantages of that is we can now use the same approach for very different types of models. And that's one of the big benefits of deep learning. We have very different types of tasks, but you can always use the same type model and like just learn it. So you don't have to put the work into what is like a good model, but the model, like you have this type of network which learns it automatically. Furthermore, it's very easy to integrate more information. So if there's other things which are important, you can just put them as your input, represent them there, and the model learns to whether and how important there is. You also don't have to say how important they are, but it can learn. But you need to have these information that you already see for all your data points, which may be sometimes a problem. Maybe some information that you have in test case, you only have for some of your training data, and for others you don't have. And then things, for example, get already complicated because you always have to have this fixed size input, and that might not be always the case. But one, essential challenge definitely is that we need a fixed size representation. And that is, of course, not always like the case. And here are just two examples from like more speech and language processing, but in general, that's in a lot of scenarios. We can't represent all the thing we want to use for doing our task in a fixed size. So if you think about a sentence, it can be, I like the lecture, I like the neural network lecture, I like the neural network lecture very much. These are not all the same sentences, but they're at least related. And they have all different types of lengths. So you cannot like somehow encode them easily and do something. So if you want to be able to handle all these inputs, you might need some type of different architecture to do that. The next, another example is audio. If you think about it, I just did you an example with audio, but I did one specific restriction there. I said we put in a 10-second audio snippet. So it has to be always 10 seconds. For speaker identification, that might be fine. We can just cut 10 seconds out of the speaker and use that to do the identification. But if you now think about speech recognition, the way you transcribe it, it might no longer be that easy. You maybe want to have the full utterance. Or, just cutting it randomly into 10 seconds might not be helpful because you need additional context. Also for the image, I did like a restriction. I said, oh, you have to scale it to n times n. Might not always be the best if you're like doing it too big, you're rescaling, so it's inefficient. But if you have a bigger image and scale it down, then you lose information. So it's somehow a restriction to say we always have to have the same size. And therefore, it would be nice if we can represent also sequences of structures of fixed size. So while we are still doing that, if you have a sequence or a structure, each element has to be fixed size. So if you have a sequence, each like element in the sequence will have to have a fixed size, but the number of elements doesn't need to be. If you think about a 2D structure, like an image, each pixel has to have like a fixed size representation, but not the overall structure. And that is definitely one thing which we need to address. Another example where it is where it's challenging is if you think about object detection. If you want to detect somehow new objects, or at least enable it to easily add new objects, maybe we have to train a bit, but it would be somehow inefficient when now you find out a new object, you would have to learn everything new. You forgot everything and start completely new. That's how we did it in machine learning for a long time, but it's not really efficiently. You want to have like a model where you can add something. So you have a model which can detect maybe dogs, cats, and rabbits. And then if you find out, oh, there are also foxes, might be bad you have to train completely from new, but can't you have a model where you can just tell them, oh, this is a fox, and then you can just continue and don't have to retrain everything. So, and in order to do that, the idea will be that instead of like predicting the classes, we are comparing it to some references and seeing what is the most similar thing. Secondly, it's not only about the fixed size representation, it's also about the input structure. So for the image, we saw an example where you can do like scale everything to a fixed size images and then put it into. However, then you have to learn some patterns for each position within the image. So just imagine you're doing like you're doing cat classification, and you have these 3 images of a cat. Each of them from a pixel look completely different. So there you have brown on the top left, there you have brown on the bottom, and there you have brown on the top right. So if you think about the network architecture, the model cannot like learn, oh, this is like how a cat looks like, and then it can be anywhere on the image. But it has to learn, oh, this is how the cat looks on the top. This is how a cat looks one shifted to the right. And then you have to completely learn it again, how it looks one shifted to the right, and so on. So it's not really efficient. So the question is, can we have architectures that learn this more shift invariant, that you just see, oh, I want to recognize this pattern, and it's not like important where it is. Of course, There might be effects where it's important where things are standing, but you should be also able to recognize patterns like somewhere in the image. And the same thing is true for text. So you want to have a structure where if you now see these sentences, I walk today, I walk today, I will walk. You have some of these I walk, which you should recognize, but it's always a different position. If you would now put this, it's like the 4 and the 5, it's like I walk. And if you put these now, even if you would now extend things to always having four things, then your inputs would always look completely different. And you would learn what does it mean that I walk is in position 1 and 2? What does it mean that it is on position 2 and 3? And what does it mean it's in 2 and 4? So of course, it would be again nice to have a bias that, yeah, generally it might be helpful to do this type of things in a more generic way. And all these challenges lead now to that we want to have different additional model types to do. What are we interested in? So in order to handle all these cases, we have to address 3 main challenges. The first thing is, how can we represent our input? Until now, we only have fixed size input. Question is, can we do network structures that can handle some of sequences? And that we will look at the basic idea of that today, and then in the next 3-4 weeks have concrete implementations of how that can be done with CNNs, with RNNs, self-attention, and so on. We will look into, and the sequences can then, of course, be extended. How can you represent n-dimensional input, and how can you represent maybe graphs or things like that? Then, if you have no more complex structures, you might want to have different types of mappings between your input and the output. Like for our classifier, it's somehow clear if you have a fixed size representation as input and output is like somehow a 1-to-1 mapping. You maybe have a fixed size reduction. So from an like a 5-dimensional input to a 3-dimensional, but it's like always a clear 1-to-1 map. If you have now a sequence, it's no longer clear. You might want to reduce the complexity. That's what is called pooling. So while you have a sequence as input, you want to either have a shorter sequence or even like a fixed size element as output. If you think about the speaker ID, it might be that you want to have variabilized input, but the output is always a class. So you can do that local. What I mean there is like by a constant factor. So reducing by a factor of 2, 3, 5 or anything, or globally reducing to 5 elements or something like that. In addition to like making things simpler, you want to also make complex structures. So you want to generate, you want not only an input handle sequence, but you want also to be able to generate sequences or images or anything. So how can you generate a structure? And then we want to look at comparison, meaning that if you have not a fixed size of class, how can you do that you can handle these different types of classes? And then, like at the final part, we will look into data, meaning that, yeah, the standard thing is supervised learning, a prediction, but sometimes you won't have exactly this data or a training scenario, and there we'll look at autoencoding and GAN style things in order to have different setups of how you use your data. But let's start with the input structure. So just as a reminder, this is the standard things we had. The standard thing is that we are having an input and output, and both of them are fixed size, and we're somehow putting our network in between. That's what we have. So how can we extend that now to handle sequences? As I said, when we're talking about sequences, what we're restricting ourselves is that we have a sequence of fixed size elements. So instead now of having one, the model should be able to handle different text lengths. How would you now represent each individual element in this sequence? Any suggestion? Yes?
On hot encoding with reference to a dictionary?
Yes, exactly. So you would do again a one hot encoding. So you can see a word again as a categorical value. if you have a predefined dictionary, so a predefined number of vocabulary. So in each item, you're not saying you can have like any word, but you have a predefined set. So you can be 5,000 choices at the first, at the second, or 100,000. But you define a vocabulary, and now you have a 100,000 dimensional vector at each position. So it's the same at each position, but the number of positions should be independent. So that would be the text case, so that you can handle variable size input, and you can put this one in there, this one in there, or this one in there. So different lengths. And the same thing goes for audio. So again, there would be an audio. You somehow cut your audio into parts, and each part is then used in there. So can we do architectures in order to do that, that we can handle these types of inputs? The question is, how can you do that? And there's two views on that, how you should view it. The one idea is you look at the local views. So in order to process now here this third element, we'll try to do a network which processes this third input. So you mainly apply your network several times, but you also want to incorporate context, because if you think about this now as a word again, of course, the meaning of a word does depend on the other words around it. So you want to have an architecture which not only looks at the current word, but also on the previous and the next word. So again, the idea is, yeah, we're building our architecture, and we're keeping our fixed size representation by just looking always at one element at a time, and maybe we're looking at the other elements in there. And that's one possibility of incorporating the context. So that you're incorporating the context because you need to like understand what the word or this token means within the sequence by not only looking at this one, but also on the previous one and the next one. And then we'll have later as what is called the CNN or TDNN. The other way of integrating context and like understanding things is, oh, maybe it helps to get a representation of the previous part and also integrate that. So you're representing your previous sequence in some type of network or hidden state, and at each time step, you're inputting your current input and the previous one into there. And always try to add that. So one important thing is now in both of these cases, RNN, CNN, also self-attention, the local view is, yes, we're doing the same processing at each time step. So somehow we're mapping it again to a fixed size representation by just not doing one calculation each time. If you have a sequence and not looking the whole sequence as an input, but we are looking each element as an input, we are processing it, and then we need, of course, to integrate the context again. So we're handling variable size inputs by doing the same processing at each time step and just handling them different inputs. That enables us then to handle this variable, because how we handle variable size input is that we're doing the processing several times, and we're doing exactly the same processing. We're integrating the context by looking at what we have processed before, or by handling input. So that is the one view on that, how you can have it. The other view is more a global view. So we are not looking at the individual tokens, but we are now handling variable size input by copying our network several times. So we're just having the same type of network, not only once to process input, but each position has the same type of network. And that can then be processed. Then again, we can do variable size input, because now we can always make our network as long as we want. If we have 3 elements, we process the 3 in parallel. If we have 5 elements, we put the 5 elements at once. The difficult thing is now, how can we do that? Because now we have different number of parameters each time. If you process 3 elements, you have 3 times the parameters. If you have 5 times the elements, you have 5 times the elements. And this is going via parameter sharing, meaning that, yes, we have 3 times this network, but all the networks have exactly the same parameters. So you're just making it flexible so that you can handle variable inputs by having like multiple times the same parameters, which is then referred to as parameter sharing. Again, so these are the 2 views. If you have a variable, and the implementation is actually the same, you can view a CNN and RNN this way or the other way. Either you can view it that you do the same calculation at each time step, you apply your network several times, or you multiply your network for each input and apply it then in parallel, and you're keeping or making sure that all the parameters are the same. This is more like what we had before as applying each input to the network several times. If you more look at it in an RNN style, what you mainly do is, you're processing the first input by the network, and then you're processing the second, and that gets input from the previous one and the current, and so on. So you're processing every time for each input, you're using the network or you're copying the network, and then the input from one network is always, the output from one network is always also used as input to the next. So what you mainly, or how you can address to handle sequences of input is by multiplying or duplicating your network or processing the sequence several times, which in the end is exactly the same calculation. It's more like how you view it. Either you view it as you take your input, you copy your network several times and process all things in parallel, or you just take the same network and apply it several times to each of the inputs. And then we don't need more parameters, but we can handle variable size input. And it also motivates you why it's important that each element, of course, needs still to have a fixed size representation, because in each input time, we put in the thing into the same type of fixed size representation. And these are then leading to architectures like time-delayed neural networks, convolutional neural networks, recurrent neural networks, self-attention, and state space models, which we will have a look at in the next weeks to come. Any more questions to this type of processing? Yes?
What's the relationship between the embedding and the structure we learned?
Between the
Embedding and the structure and the several model.
the embedding.
Yeah, the input is not embedding, or the output is embedding.
I mean, as an embedding, you typically mean, or you understand that you have a categorical thing, and then you map it into a more dense representation. You also apply that as each time step, but the typical thing of an embedding is that there is no connections between them. So now we talk that you want to integrate context to make more understanding. The embedding is similar to that, except that you do the same application each time, or you copy it, but there's no information flow between the different elements of the sequence. While here you add in different ways information flow, either by at each time step looking at several inputs, or by processing or using the inputs of one step into as output to the next step. Okay, so with this, then let's scale things and think about a bit more complex structure. So what we can now extend that, of course, is to like an n-dimensional input. So just imagine you have now an image which would be 2D, and the most straightforward way of doing that is you can linearize that as shown here. You can just put the image there into a sequence of things and use as input. What you need is, of course, you want to have a bit of additional context relation. So you either have in your CNN, if you do the context, you're not only telling it like the green, blue, and then blue, or blue, purple, and then purple, red, because that would mean somehow you treat these two relations as the same. But normally you would treat that, for example, the relation between green and blue is the same, and between purple and orange, but the relation between blue and purple is different. So that you can now do, if you think about this type of networks, in like how you connect the architecture. But again, in that you can do it the same way by like now applying your network at each position, or copying your network at each position, and then encoding which information you put into each of these types of calculations. And you can do that, of course, even further. So if you think about graphs, what we did until now is like sequences and grids. That's 1- and 2-dimensional. But in generally, you can generalize that to any type of graph, meaning that now you again process each node individually, or you copy your network to each node and do the same calculation, but then what information are needed, it might be more complex. So before in a grid, it's in the sequence, it's like clear what neighbors you have. You have a left and right neighbor, and you can put them in. In a graph, things get more complicated in like you will maybe want to include the weights, and there's different number of neighbors per each element. That makes, of course, things difficult. If you think about it again, if you have a structure where you put in your neighbors somehow in there, you again have to assume that you have the same number of neighbors at each position. Here it doesn't work, so you might need to average information, so you have a fixed size. But in general, it's again the same idea. You apply your network at each position and somehow model your context in a way. Maybe one thing for the last two, if you more think about the RNN style, things get a bit more complicated, because if you think about, you put the input at one calculation as output to the next, no, the output of one calculation as input to the next, then you need to have a clear sequence of how you process elements, because the input of one is the output of one is the input of the next. That is, in a sequence is quite clear. You go from left to right. That's somehow natural. To think about a graph or even already a 2D image, things might be a bit more complicated. There are ways of defining that, but it's not like as clear anymore as you have that in a normal sequence. So all these types of networks, what they are doing is they can like model these types of mappings. So from one element to one element, or they can do from a sequence to a sequence, from a grid to a grid, or from a graph to a graph. Allowing us to now not only process fixed size input, but somehow variable size inputs, where each element, so each node in there, has somehow a fixed size representation. Good. Any questions about that? Yes.
So the dimension of the output is defined by the length of the input sequence, right?
Not only also the length of it. So here you have also a fixed size output sequence, a variable size output sequence, and the sequence is the same as the input. Okay. Yeah. So you cannot change it. We'll come back. That is what I summarize under mapping. Where look, if you have problems where your input sequence is different than your output sequence, we need to do something else. This is really only learning a one-to-one mapping somehow. The dimensions can be different. So I mean that is like in a normal network, it can be that here you have a sequence of elements where the input is like 100 dimension, and then you can easily build a network where the output dimension is 200 at each element. But since you apply the network at each element individually, or the same network at each, you have to have the same number of inputs and outputs. Yes?
So these dimensions have orders.
Yeah, they have a meaning. So you cannot like randomly, I mean, you predefine the first dimension means this, because this is like, I mean, you do a matrix multiplication for that. So if you randomly switch the dimensions, you'll get different results. Good. And with that, go to the second part and the mapping a bit, because it might not be always the case that we want to have an output sequence which has the same length as the input sequence. So for some, this one-to-one mapping is is important. So is fine. So if we think about our weather casting, anyway, this is like a one-to-one mapping. And so there is no additional layer and somehow necessary to change the dimension. What we can do is like, we can have different dimensions here, but the number of elements is the same, since in this is anyway, we have one element as the input and one element as the output. There is no need for two. Even for sequences, that is sometimes not needed. If you think about something like part of speech tagging, maybe you know that from high school, where like there's nouns, verbs, adjectives, and so on. If you want to build that, you have a clear one-to-one mapping. For every input, you want to have exactly one output category. The number of categories, it's different. So you have a lot less attributes and the part of speech and vocabulary, but that is possible. But you have a clear one-to-one mapping for each input. You have one output. Therefore, you can again do like what we already have, and that is possible. However, not all of these are working. And the most simple thing about that is, yeah, you might want to change the length of the sequence. And that is like shorten. I mean, you want to shorten it, or you can also like extend it, but there is a clear correlation between them. If you want to do pooling, the first thing is you can do local pruning by doing like by shrinking by a fixed factor. That is typically possible just by assuming, again, if you now think of that viewing again, you're copying your network n times. You're not copying it n times, but n half times now, and each one gets 2 as an input and 1 as output. Then you can shrink your thing. You can also extend it by having 1 input and 2 outputs for that. So by changing the length here by a fixed size, that is somehow straightforward. You can also view it in the other way around. You get here an n-dimensional input. Either you always merge 2 into 1, then you have a double size, or you like split them up. So if you have a fixed factor, that is straightforward possible. And it's applied in a lot of things, because the computation time depends often on your sequence length. So if you can do pooling, you can make your sequence shorter and therefore be more efficient. So it's an important tool, but that you can do with these types of networks. The other thing you want to do is you maybe want to have global pooling, meaning you want to like reduce a variable size input to a fixed size. That is also possible. So the idea is you want to summarize everything into one signal. You can view that as, for example, if you think about a sentiment analysis, you want to classify a sequence. It's also for object detection. You have an image as input and you have just some classes there. Then you need to do some type of pooling which removes the variable size. And the easiest things are things like mean or max pooling. Just meaning you calculate your calculation at each time step. And then for each dimension, in each element, you either take the maximum value, the mean value, or anything like that. So it enables you to handle, like go from variable size input to like a fixed size representation and doing that. What it really means is, yeah, removing the structure from your input. So you have a complex structure input, and now you're removing it and have a fixed size, simple representation. So that is possible by operations like mean or max or something like that. Any more questions to this? Good, because then we can go, of course, for the like a bit more complex stuff. I mean, removing information is often easier. So you have a complex structure and you just collapse it into like a fixed size representation. But you might also want to generate some type of complex structure. I mean, we are focused on the more easy thing, which is a sequence. So we said the sequences has to be the same length, but it might be you want to have also the ability that you get some input and you generate a sequence output. And of course, it's correlated, but it's not an easy correlation. It's not like if the input is 1, the output is always 1. If you again think of something like, for example, yeah, we come to some of them. So you want to generate a new structure, and that can be the easiest, and what we're coming out with is a sequence. That can, for example, be the problem of image to text. So image to text means you want to generate subtitles. You want to describe what is in the image. You give it an image, and then it should say something, an image of a cat. So similar, if you see it in books and papers or so, you have the image, and it should automatically generate what should be a description of that. If you want to have this task, you have like an image as input, and you need to generate an image output here. And it's not easy to know what is like the right output, and not for the same output size, you always have the same input size, you have the same output size. So even if all your images are the same, sometimes you're like pixel-wise, sometimes you have longer descriptions and shorter descriptions. But also if you have different images, different sizes of the same image, your input representation is different, but the text output should be the same. So there is, of course, like they depend on each other, but it's not purely as a size. It's also based on the content on what you describe. Another example of that is the machine translation. So if you translate from English to German, it's not that you always have nicely like here forward input and forward output, but it can be that it's like the German text is shorter or longer than the English text, again, depending on the content. And so also in this type of task, you have to add some type of ability that you can produce different types of output lengths depending on the input. And if you think about that, there's different types of challenges with that. So the main additional challenge that we have is we not only need to predict now the content. So you not only predict, oh, the third word is I, the fourth word is walk, and so on, but you also need to predict what type of structure do you want to have. And predicting structure means in this case, you have to predict what is the length of your sequence. So it can be that your answer is 2 points, 3 points, 4 elements, and so on. At least in sequences, that is easy. The only thing of structure that you need to predict is the length. You don't have to predict how they are connected, because that's always the same. But at least the right prediction of the length is what you have in this additional challenge. You not only have to predict the value, as we had before, but you also have to predict the structure. And this, of course, makes things more challenges. And so you need to have models which can also do that. And the difficult thing is that the structure is, of course, strongly correlated with the content that you're doing. If you have an English sentence, you can translate it into 3 or 4 different or more, but I mean, several different German sentences. And depending on how you phrase it, your structure will also be different. So depending on what words you use at the beginning, you need different lengths of the sentence. And therefore, what is the good way of doing it? And we'll see, in order to do prediction, what is typically done is what is called autoregressive. And that is, again, if you have to predict a complex structure, might be good that you just do it step by step. So at each step, you decide, okay, what is the best next element to predict? You're predicting that element, and then you continue. And the important thing, that's why it's called autoregressive, you're telling the model what you predicted last time. Because what should be following up depends not only on your input, but also like how you started. So how to continue a sentence depends on how you started the sentence and what your task is. So that is why it's autoregressive. You're always inputting the model again. Oh, this is how you started. How do you want to continue? Allowing the model also to like generate different types of input. So in order to generate new structures, the most common approach to currently used in, for example, also large language model is this autoregressive. Again, by using, it's similar to the input. You're also like doing one step at a time, but this time you're generating one output step at a time. And the important thing is you're also inputting the model what you did last, so that you not have to predefine oh, I will generate it. You're not doing this. You're not first predicting, oh, I'll generate an output which has 5 elements, and then you generate the 5 elements, but you're generating 1 element, telling the model you've generated this, and then you're doing the next step. So there's only one question: how do you stop? Does anybody know already what is a stopping criteria? Yes?
We can have a specific output that just signals the stopping.
Yes, exactly. So that typically you have a specific stop token, and once you generate this, you will stop further production. And this enables you to like not having first defined the structure and then the content, but since they are so strongly connected, you're doing both. You're generating the content and you're predicting the structure. And therefore, we'll have different types of models. So there's like mainly 2 types of architectures which we'll look at. The one is what is called the encoder-decoder architecture, where the idea is we have one type of network which processes your input and tries to understand what is in the input. And then you have the decoder, which does this generation process one step at a time, always trying to understand what it is and then generating like each token to do your new step. That is what is referred to as the encoder-decoder model. The other type of model is the so-called decoder-only model, where you have the same model which first like processes step by step, as we've done before, the input, and then just continues, and now not only like processes the input, but also generates the output there. And as input always uses what it has generated before. Yeah, so this is like then you're very similar to what we had before. So you can extend now to generate new structures by just always generating the structure step by step and inputting the previous one into the next step. Good. Any questions to this type of mapping? One limitation which we haven't addressed. So what we can now do is, okay, we can generate now different types of structure. However, there's still one limitation in there, that we have a fixed size representation at each element. So at each time step, we have to select or generate a fixed size type thing. And that means also we cannot learn something completely new. So we cannot say, oh, now you have foxes and you can recognize foxes, because you have predefined that you only have these types of elements to do. So if we want to do something like that, that we recognize new elements in an image, we have to do something else. So as if you have our network, we are putting in here our image. Here our image, and then it would be nice that we can generate our output there. The same thing is, of course, not only for sequences, but also for like if you do speaker identification, you have a sequence of audio, and now somehow it's said that you once have to define these are my 10 speakers, I can recognize them, and then you cannot like easily add a new one in there and also handle them. So the question is, how can you do that? That it's like very easy to add new types of speakers in there in order to do that. And this is, of course, also possible, and this is possible with what is called Siamese networks. And what is the idea? Instead of, before we're trying to predict, oh, we have this type of predefined set, and we want to predict which one out of them is that. The idea is now if you have more variable input, so an image, you just can take image of different objects and you can easily add more objects. So the network should no longer learn which object it is, but we are changing the task into, is it the same object or is it a different object? So we're putting in a cat and a dog, and then it should learn that this is a different type of object. If we are putting in two objects, it should put in two dogs, it should predict that this is a dog, and this is the same. So you're mapping now like a open class problem into just a binary decision. Is it the same or is it not the same? And then again, you can have this type of network structure. And now it's only like how many elements you put in there. So what you really try to do is like you want to somehow calculate the cosine similarity. If it's very similar, you want to have a representation that when it's very similar, then it's the same object, and if it's very dissimilar, it's not the same. And now the nice thing is you're not having to predefine anymore how many objects you can recognize. Hopefully it will generalize, because it's also not perfect. If you always train it only with cats and dogs and then you put in a penguin, I'm questionable whether that will work. But it should generalize a bit better, and especially if you train it in a lot of them, it might recognize also some other things. So instead of like predefining, I want to recognize this, what I'm doing is I'm doing it into a comparison by saying, are these the same or not? Because then it's a binary decision and not like an enfolded decision. And yeah, then of course, for your reference, you not always have to calculate anew. You can also just, again, you can interpret this as an embedding, or so you learn once a representation for this type of object, and then you can just compare. So at inference time, what you only have to do is that you compare your reference images to your input, and then you select which one is the most similar, or is one similar enough. That depends a bit on your task. Then, if you're doing that, there is a dedicated type of loss for that, which is called this triple loss. So what you're trying to learn then is like, if you have here your example, your answer, you have positive and negative images, then you're having a loss which tries to move your positive images near and move your negative images far away, so that you have like a maximum margin here between your positive and negative images. So your aim is to learn really this good yellow embeddings, so that's easy to determine whether two things are similar or not. And then you can put in like always two images and decide whether they are some of the same object. Again, it's like a reformulation. So before we had it, if we have variable size input, we're just treating it several times. Now we're saying if we have variable size outputs, we're just doing a comparison instead of doing a clear classification of what it is. So with this, what we saw is there's different types of mappings that we can learn and where we need dedicated solutions. We can do this one-to-one mapping is a standard that's what is working with normal networks. And we can do pooling, which will allow us to remove the structural information and go to a fixed size representation. We can have models which do generation, which like generate some type of sequence out there. And then for the last part, what we can have is if we have want to like have not a fixed size like element-wise comparison, but like having a set of things that we can recognize, instead of like directly predicting what it is, we can do like a comparison and then try to, instead of that, learn to compare instead of learning to directly predict what we have. Good. Any more questions? Yes.
If you go back to Siamese networks,
Yes.
If I train this model with only cats and dogs,
Yes.
and I throw in for the inference a penguin,
Yes.
then the model will tell me this is neither a dog, this is neither a cat, but it couldn't tell me that it's penguin.
I mean, hopefully it will tell you that if it's only in two, yeah. By what it could do, you once put in one penguin, and then if you have another penguin image, and so yeah, you once see a penguin, so you tell the model, oh, this is an embedding of the penguin, and now you're going out to the wild, you apply the model, now you can compare it to the dog, the cat, and the one penguin you have, and you can decide which one is the most similar. I mean, maybe it's not very good trained for penguins, so if you have only trained it on 2, it will not work well. But if you're trained on a lot of classes, then you can extend it to 1 more. So the nice thing is, yes, you need 1 example of the category to categorize it. That is true, but you don't have to retrain your complete network. You don't have to learn everything. If you're getting a new category, you just need to once do the forward pass to learn the embedding of that category, and then you can also do that. Of course, this is a bit idealistic. So, I mean, if it was 2, it won't work, but it's more like, yeah, if you have 1,000 objects, you now got the 1,001 object, which maybe is not completely irrelevant, but some variation of that, you can add that object and also do that. I mean, the same thing, maybe it's more clear if you have speaker identification. So you want to know who is speaking. So you need 1 sample from each speaker. If you now have 20 speakers, you can identify them, hopefully. If you add now the 21st speaker, hopefully you will say that this, if you now got the same sample from that, you will be also able to recognize that. Yeah, but it's a very good point is, of course, yeah, you need 1 example from the new categories. The thing is, you don't have to change everything. You don't have to even retrain. Good. So then for the last minutes, let's have a look how you can train them. It's only very brief overview, but just a bit on the end. So the most common thing we are training and will be training on is like supervised data, meaning we have examples of the input, we have examples of the output, and we are just doing the prediction. We will see later that this is very powerful and is even good for data where we don't have pairs of input and output. What we are doing there is we're just inventing tasks, and that is then called self-supervised learning, where we are putting some part of your input as the input and other parts you mark as your output. But this is like the standard thing. You know what your model should do, and then you're exactly training the model to do what you know it should do. But of course, there's also other tasks where you can try and where it's successfully used for that. One thing is the type of autoencoders. And there the idea is you have pairs, and this time it's input. And you put in your input and trying to reconstruct your input. So you're training to do that. The nice thing is that can be done in an unsupervised way. And what you maybe want to do is you want to learn a good representation of this model. In a way that, yeah, if you're somewhere in between, take the activations, all the information about this object should be in there because you can later create it itself. And hopefully then this representation is a very helpful one. The problem is, how can you now force the model in order to learn like useful representation? And there's mainly 2 ways of doing that. On the one thing, you can do some type of compression, saying that in between you're making the representation smaller, and then you're learning a representation that is a smaller dimensional, but since you need to reproduce things, it's working quite well. The other case is you can add noise, so you can disturb your input and train it then to reconstruct it. Then you hopefully also learn a representation that is robust against some noise, and this might be helpful. This then already goes very much into the direction of self-supervised learning, where you somehow change your input and predict and maybe parts of your output, or you can predict everything. Another way of using models is to combine different models to somehow play together. And then their famous example is what is called generative adversarial networks, or GANs, where the idea is, yeah, you want to have one model which generates you examples, and you want to have these examples to be like as similar as real examples. So you have some noise, and then there's a model which, based on this noise, generates an object. And this should be now very similar to your real objects. So you want to have a model which generates real images or something like that. How can you make that, or how can you make that this and this looks the same? And again, therefore, maybe we can just build a neural network which decides or like do that. And then you're doing so now, then you're training here your discriminator, where you give in either a real image or you give in a fake image, and the model should determine whether it's real or fake. And now you can play a game where they play against each other. So you try to train the discriminator in a way that it's very good in discriminating between real and fake images. And then you train the generator in the opposite way. So that should generate images where the discriminator can no longer discriminate between these two. And then if you train them long enough, you get hopefully a thing which can generate very good fake X, for example, fake images, where the discriminator is harder and harder for the model to learn. Problem is, this is a bit unstable, so it's not super easy to train it, but it's a quite successful approach and has been used for some time. An extension, of course, I mean, generally it might be a bit boring to just generate random stuff. So normally what you want to often have is a conditional gun. So you want not to generate anything, but you're saying you have a fixed size of classes, and then you want the image to generate one of these classes. Of course, there's like variation of that, and then the model can distinguish. So for example, you're saying, again, if you have cats and dogs, you want not an image generator for anything, but you want to take the image generator, now generate a cat, and now generate a dog, and then it should generate this one, and the discriminator should not be able to discriminate between these two. How that then looks is, here are some examples from such a work. So you put in an input and then you can reconstruct it. You put in edges of a photo and you can generate then real photo. And then again, it's like, so this is your condition, the left one, the right side is what it's generated. And so you can generate a lot of artificial data. And if your discriminator is good, then the generator also has to be good in order to like really produce images where the human also cannot easily do that. Good. So, any more questions? So to summarize, what you should like keep in mind from today is, okay, we looked at different classifiers. We looked how you can put data in there, how the data processing is working, and then we looked at the limitations of classifying, telling you, yeah, with pure classification, you can already address a lot of interesting problems, but there's a lot more problems where this is not enough. In order to do that, you need to, on the one hand, handle different types of input structures. We looked how you can do that on sequences and on more complex structures. And then you also, once you have complex input structures in the model, you might also want to learn different types of mappings. So you want that you not only can map a one-to-one mapping between a complex structure at the input and the same at the output, you want to like remove the structural information, or you want to generate other types of structures. And we got to first say that you have to do it. Or it's not only about structures, it's also about content, that you want to like generate different types of content. And finally, we looked how to train. Based on that, we'll now look, especially like on the structural input, as I said, what are the concrete implementations of that? We'll start next week with RNN and TNNs or CNNs, which are more basic, and I guess some of you have already heard. And then next week, we'll go further with self-attention networks and with state-space models. With this, if there's no further questions, thanks for joining, and then we'll see each other again on Thursday.